Hello and welcome to this 24th set of problems on complex numbers. So in this set we will study problem number 231 to 240. Now there are two changes which I have made. If you are observant, the title has changed from Dayal to Dashru, and the second change would be from the next video. So this presentation is made up of slides using LaTeX. So I make PDFs and then I record the videos. After this, you see that I give the link in the description of the slides. But after this, I will make the slides in HTML, CSS, and JavaScript, and I'll upload those to my website. So when I'll create the videos, you will see that what links I'm following so that you can go to the slides later on after watching the video for your reference. So these are the two changes which are going to occur. First, I have changed my name. But it's a big change, but it is not yet legal, but eventually I'll get there. So as always, I will repeat that when I'm reading the problem, you should pause the video and try to solve the problem yourself. Only if you cannot solve the problem yourself, you should look at the solution. And even when you look at the solution, try to understand it and do it yourself. First, read few lines, see if you get the hint, try to do it. If not, then look at the full solution and do it. But what you should do also is, if you cannot solve the problem and you have looked at the solution, 15 or 30 days later, you should revise it and then try to do it yourself. That is, when it has gone out of the solution has gone out of your memory, you should attempt the problem again. Okay, this will help you reinforce the problem solving techniques, because that's what mathematics is all about. It's all about problem solving techniques. Okay, so without further ado, let's get started. Question 231 says that if mod z less than equal to 1 and mod of w less than equal to 1, so that mod of z minus w squared less than equal to mod of z minus mod of w whole square plus argument of z minus argument of w whole square. So we use polar coordinates for this because arguments are involved. So we have let mod z is equal to r1, mod w is equal to r2. So z argument of z is equal to theta 1 and argument of w is theta 2. So mod z minus w whole square would be, there is a mistake here. So this should be r2 cos theta 2, and this one should be r1 sin theta 1. There is an exchange of terms here to make. Sorry about this. So mod z minus w whole square is equal to r1 cos theta 1 minus r2 cos theta 2 whole square plus r1 sin theta 1 minus r2 sin theta 2 whole square. This won't change this result. This will be mod of r1 minus r2 whole square plus 2r1 r2 minus 2r1 r2 cos theta 1 minus theta 2 whole square. Now from trigonometry, we have an identity that is 1 minus cos theta 2 is equal to 2 sin square theta. So if you take 2r1 r2 common, it will become 1 minus cos theta 1 minus theta 2, which would be 4r1 r2 sin square theta 1 minus theta. This term remains same. Now from trigonometry, we also know that sin theta is less than equal to theta. So we remove the sine function from here and we write as r1 minus r2 whole square plus 4 theta 1 minus theta 2 by 2 whole square. 2 square will cancel 4, so this will become mod z minus mod w whole square plus theta 1 minus theta 2, and theta 1 minus theta 2 is nothing but rz minus rw. Question 232 says that if z is any non-zero complex number, show that mod of z by mod z minus 1 less than equal to mod of rz and mod of z minus 1 less than equal to mod of mod z minus 1 plus mod z multiplied with mod of r. So again, we use polar coordinates because argument is involved. So we let z is equal to r cos theta plus I sin theta, by which is equal to z by mod z is equal to cos theta plus I sin theta. Therefore, mod of z by mod z minus 1 would be mod of cos theta minus 1 plus I sin theta. Now we take the modulus, and like the previous example, it becomes 4 sin square theta. It's the same identity. Two identities are used here. Sin square theta plus cos square theta is equal to 1. And 1 minus cos 2 theta is equal to 2 sin square theta. Two identities are used. We have got this. And this is equal to 2 into mod sin theta by 2. And like previous problem, sin theta less than equal to theta. So this is less than equal to mod of theta. So this proves the first part, that is this part. Okay, now we go on to second part. So first we evaluate z minus mod z, which is okay, it's not even here. Okay, so what we do is we take mod of z minus mod z, we subtract one from both, so one will get cancelled. So this would be greater than mod of z minus 1 minus mod of mod z minus 1. Therefore, we can say that mod of z minus 1 minus mod of mod z minus 1 is less than equal to mod of z minus mod z. Now this z minus mod z is nothing but r cos theta plus I sin theta minus r, which is nothing but r mod of theta. Calculations are similar. This is nothing but mod of z into mod of rz. This is the last part. Therefore, we can say that mod of z minus 1 minus mod of z minus 1 mod of mod z minus 1 less than equal to mod z into r z. From here, we can say that mod of z minus 1 less than equal to mod of z minus 1 plus mod of z into r z. You see, what we have done from taking this is we are evaluating mod z minus 1 minus mod of mod z minus 1. So that's how we have proceeded here. So that's a nifty trick you can see, because this is rz is involved and there is no rz in these two, so we combine them together and then we evaluate. Question 233 says that if mod of z plus 1 by z is equal to a, where z is a complex number and a greater than 0, find the greatest value of mod z. Now we again let z in polar coordinates, that is z is equal to r cos theta plus I sin theta, then 1 by z becomes 1 by r cos theta minus I sin theta. Now we are given that mod of z plus 1 by z is equal to a, so it becomes r plus 1 by r cos theta plus I r minus 1 by r sin theta is equal to a. So we take the modulus, we have r plus 1 by r whole square cos square theta into r minus 1 by r whole square into sin square theta. Now we simplify this, it becomes r minus 1 by r is equal to a square minus 4 cos square theta. Okay, so once we have this, we will have cos theta is equal to 0. Cos theta is equal to 0 we have taken so that this is greatest value. Okay, it won't be greatest when cos theta is minus 1, because that will make cos square theta positive, so this will be greatest when cos theta is equal to 0. So we arrive at r square minus ar minus 1 is equal to 0, which gives us r is equal to a plus minus square root of a square plus 4 by 2. Now observe that we have cos theta is equal to 0. That means the real part will become 0. So the number z is purely imaginary number. Question 234 says that if z1, z2 are complex numbers and c is a positive number, prove that mod z1 plus z2 square less than equal to 1 plus c mod z1 square plus 1 plus 1 by c mod z2 square. So what we do is we have mod z1 plus z2 square less than equal to mod z1 square plus c z1 square plus z2 square mod z2 square plus 1 by c mod z2 square. So we use the identity mod z square is equal to z bar. We write this as z plus z2 into z1 plus z2 into z1 bar plus z2 bar less than equal to mod z1 square plus mod z2 square plus c square mod z1 square plus mod z2 square by c. Now you observe that z1 bar will become mod z1 square, so that get cancelled. z2 into z2 bar will become mod z2 square, so that will get cancelled. So we will be left with z2 z1 bar plus z1 z2 bar less than equal to 1 by c into c square into z1 square mod z1 square plus mod z2 square. Now we substitute z1 is equal to x1 plus iy1 and z2 is equal to x2 plus iy2. So we have this, and the right hand side is this. And once you simplify this, you multiply this and cancel out terms. Okay, and you add terms. For example, x1 plus x2 will become x1 into x2 will become x1 x2. iy2 into iy1 minus i1 will become y1 y2. Similarly, here we will have x1 x2 y1 y2, so that will become 2x1 x2 2y1 y2. Similarly, x1 iy2 is here positive. Here x1 iy2 would be negative with I, that will get cancelled. Similarly, x2 into iy1 will get cancelled here with plus iy1 x2, that will get cancelled. So essentially on left hand side we will have 2x1 x2, 2y1 y2. That will get multiplied with c, and you can bring it on right hand side, and this will give you this result. Question 235 says that if Z1 and Z2 are two complex numbers such that mod of Z1 minus Z2 by Z1 plus Z2 is equal to 1, prove that IZ1 by Z2 is equal to x, where x is the real number. Find the angle between the lines from the origin to the points Z1 plus Z2 and Z1 minus Z2 in terms of x. So we are given that mod of Z1 minus Z2 by Z1 plus Z2 is equal to 1. So we square it, and we take the denominator to right hand side. We have mod of Z1 minus Z2 squared is equal to mod of Z1 plus Z2 square. We use the same identity, mod Z square is equal to Z bar. We have this. We simplify, so after simplification we arrive at Z1 by Z2 bar is equal to minus Z1 by Z2. Now remember, the identity which we have discussed in theory is that if a number is imaginary, if a complex number is purely imaginary, then Z bar will be equal to Z. Okay, the complex conjugate is same as the number if the number is purely imaginary. Sorry, negative of that. Complex conjugate would be negative of the number. So from here we can deduce that Z1 by Z2 is purely imaginary. Therefore, I Z1 by Z2 would be real, which we have taken as x. So that proves the first part. Now to prove the second part, we evaluate Z1 plus Z2 by Z1 minus Z2, which is equal to Z1 by Z2 plus 1 by Z1 minus Z2 minus 1. This is nothing but minus ix plus 1 by minus ix minus 1. So we rationalize, we have on numerator x square minus 1 plus 2ix. That's all we care about. We don't care about denominator because that will get cancelled when we calculate the argument. Now argument is theta here. In the case, theta is the angle actually between the lines joining the origin to the point Z1 plus Z2 and Z1 minus Z2. So our tan theta becomes argument of Z1 plus Z2 by Z1 minus Z2. That's why we don't care about the denominator. This would be nothing but mod of 2x by x square minus 1, which is the second part of the question. Question 236 says that let Z1, Z2 be any two complex numbers and A and B two real numbers such that A square plus B square is not equal to 0. Prove that mod Z1 square plus mod Z2 square is equal to mod Z1 square plus Z2 square less than equal to 2 mod AZ1 plus BZ2 whole square by A square plus B square less than equal to mod Z1 square plus mod Z2 square plus mod Z1 square plus Z2 square. So to solve this problem, we'll take Z1 and Z2 in polar coordinates. We also let square root of A square plus B square as R, so that R cos alpha and B is R cos alpha. Remember that A and B are real numbers. So we evaluate mod AZ1 plus BZ2 square, which is when expanded will become RR1 cos theta 1 plus I sin theta 1 cos alpha plus RR2 cos theta 2 plus I sin theta 2 sin alpha square. And once you take it out of the modulus, it will become R square R1 square cos square alpha plus R2 square sin square alpha plus 2R1 R2 cos alpha sin alpha cos theta 1 minus theta 2. Now we know that cos square alpha is 1 minus cos alpha by 2, and sin square alpha, cos square alpha is 1 plus cos 2 alpha by 2, and sin square alpha is 1 minus cos 2 alpha by 2. So we can effectively write this equal to R1 plus R1 square plus R2 square plus R1 square minus R2 square cos 2 alpha. Note that 2 we have taken outside. Now since this 2 has come outside, it will also come inside. It will make 2 cos alpha sin alpha as sin 2 alpha. So here we have 2 R1 R2 cos theta 1 minus theta 2 sin 2 alpha. So this we have written equal to R square by 2 into A plus B cos 2 alpha plus C sin 2 alpha, where A is R1 square plus R2 square, B is R1 square minus R2 square, and C is 2 R1 R2 cos theta 1 minus theta 2. Now we know that A minus square root of B square plus C square is less than equal to A plus B cos 2 alpha plus C sin 2 alpha is less than equal to A plus square root of B square plus C square. It's a standard inequality. So we now evaluate b square plus c square, which is nothing but r1 to the power 4 plus r2 to the power 4 minus 2r1 square r2 square plus 4r1 square r2 square cos square theta 1 minus theta 2. Therefore, we now evaluate mod of z1 square plus mod plus z2 square, which turns out to be nothing but square root of b square plus c square. And thus we have proved the desired result. Question 237 says that if b plus ic is equal to 1 plus a into z plus and a square plus b square plus c square is equal to 1, prove that a plus ib by 1 plus c is equal to 1 plus iz by 1 minus iz, where a, b, c are real numbers and z is a complex number. So we are given that z is equal to b plus ic by 1 plus a. So iz would be minus c plus ib by 1 plus a. So we calculate 1 plus iz by 1 minus iz. It would be equal to 1 plus a minus c plus ib divided by 1 plus a plus c minus ib. Now we are given that a square plus b square plus c square is equal to 1. We take c square to the right hand side. It becomes a plus ib into a minus ib is equal to 1 plus c into 1 minus c. Now we use these values, substitute in 1 plus iz by 1 minus iz, we get a plus ib by 1 plus c. Question 238 says that for any two complex numbers z1 and z2 and any real numbers a and b, show that mod of a z1 minus b z2 squared plus b z1 minus a z2 squared is equal to a square plus b square multiplied with mod z1 square plus mod z2 square. So we let z1 as x1 plus iy1 and z2 as x2 plus iy2. So it's a matter of simplification only. There is nothing complicated here. The first term becomes ax1 minus bx2 plus ay1 minus by2 squared. Both are squared. And the second term becomes bx1 minus ax2 whole square plus by1 minus by2. There is a mistake here. This should be ay2 whole square. Now you evaluate this. It will become a square plus b square into x1 plus x1 square plus y1 square, and it would be x2 square plus y2 square. So this is nothing but a square plus b square into mod z1 square plus mod z2 square, which is our right hand side. Question 239 says that if alpha and beta are any two complex numbers, show that mod alpha plus beta square is equal to mod alpha square plus mod beta square plus real part of alpha beta bar plus real part of alpha bar beta. So we let alpha as x1 plus iy1 and beta as x2 y2. Then mod alpha plus beta square is equal to x1 plus x2 square plus y1 plus y2 square. It is nothing but x1 square plus x2 square plus y1 square plus y2 square is equal to a plus 2x1 x2 plus 2y1 y2. Now clearly mod alpha square is x1 square plus y1 square, and mod beta square is x2 square plus y2 square. Now we compute real part of alpha beta bar, which is x1 x2 plus y1 y2. We compute the real part of alpha bar beta, which is x1 x2 plus y1 y2. Now once we have that, we can substitute that in here, and you will see it will give you 2x1 x2 when added. It will give you 2y1 y2. So x1 x2 and y1 y2 will get added here, and that will be equal to mod alpha plus beta square. Question 240 says that prove that 1 minus z1 bar z2 squared minus mod z1 minus z2 square is equal to 1 minus mod z1 square into 1 minus mod z2 square. So again we use the identity mod z square is equal to zz bar. So from left hand side we have 1 minus z1 bar z2 into 1 minus zz2 bar. And the second term would be z1 minus z2 into z1 bar minus z2. So from this we have 1 minus z1 bar z2 minus z1 z2 bar plus z1 square z2 square. If you multiply these two, you will have minus mod z1 square minus z1 bar z2 minus z2 bar plus mod z2 square. So you'll see these two terms will get cancelled, and we will have 1 minus mod z1 square minus mod z2 square plus mod z1 square mod z2 square is equal to 1 minus mod z1 square into 1 minus mod z2 square. This is our right hand side. So with this we come to the end of this set of problems, and I hope you have found this video useful and informative. So as always, it is the typical YouTuber life that subscribe the channel and like the video, and if you want to say something, if you have questions or you have suggestions, make use of the comment box. So in the next video, we will move on to the website version of problems, and I'll see you there in that. So like, subscribe and comment so that it reaches more video and motivates me to make more videos. Thanks a lot for watching. Have a nice day.